great pleasure to welcome Stewart. He's now, as I say, at the University of St Andrews. He's starting a new geocomputational unit there, which I'm sure will be equally successful. So I'm delighted to welcome you, Stewart.
Yeah, thank you very much, Graham. That's very nice. Thanks very much. I apologise for the delay as well. I'll try not to keep you too long between this talk and the evening out in Leeds, which Graham has promised us. It's a great delight to be here because I'm going to talk, as Graham mentioned, about two things in my academic career which are now coming together under this rubric of localized spatial interaction models. And that's my long-term interest in spatial choice modeling, mathematics of spatial choice and spatial cognition, with localized models through the geographic weighted regression framework. And the two come together, I think, quite nicely in this presentation. It's a very auspicious venue to come to give this talk, because I've always thought that Leeds is, always has been for me at least, a kind of mecca of spatial interaction modeling. When I sort of grew up academically, Leeds was the real hotspot in this particular topic, not just with Alan Wilson, but lots of other people, Phil Rees, Graham, Mark Birkin, Martin Clark, Hugh Williams, all the Institute for Transport Studies, etc. Most of the work in spatial interaction modeling that I remember was done here at Leeds, in the Leeds Working Paper series. I've still got quite a lot of copies of those things. So it's very nice to be able to come back to Leeds and talk again about spatial interaction modeling. Okay, as Graham mentioned, I'm director of the Centre for Geoinformatics. We have the top floor of this rather nice building in the University of St Andrews. My office is actually just that one there, that runs along there. Rather nice. These are some students who came out to greet me on my first day of work. But the university is 600 years old this year, so we have all these special celebrations going on. I need to mention it. Okay, the structure of the talk. Some comments. I'm going to talk briefly about spatial interaction models. I know most people in the room know what spatial interaction models are, but just so that we're all on the same page before I venture further. I'll talk about the localizations briefly that are standard. We all know about these, origin-specific and destination-specific models. And then I'll talk about the localizations that we may not be so familiar with, which I call fuzzy localization, although I'm not exactly sure that's the right word, but I can't think of a better descriptor for what I'm going to be talking about. And I'll explain the 5 different types of fuzzy localized spatial interaction models, and then give you an example of a couple of them. They're rather complex in terms of the output, but understandable in terms of their structure. It's quite simple really. I'm going to give you an example of their operation, their application to commuting flows in the metropolitan area of Lausanne in Switzerland. So that's the structure of the talk. And let me explain the problem first of all. Geography, I always describe geography as the study of spatial processes. That's a definition I can defend. It's a definition I think applies to all branches of geography. It's what we all do, what we all attempt to do. And the processes that we're looking at are those which generate the data we observe about the real world. That's what spatial processes are. So one useful way of uncovering information on spatial processes is to calibrate spatial models and to obtain estimates of the model or the model parameters. And spatial interaction models are examples of spatial models, very good examples of spatial models, and they're very applied. The more parameters we can reliably estimate from within the model structure, the more information on spatial processes we can generate and obtain. So the problem is basically, how do we do this? How do we go from a model which has relatively few parameters to be estimated and gives us very limited information on the processes generating the data we're observing, to a model which is more complex, has more parameters, and we can generate from them, which we can generate more information on the processes generating the data. So, for example, typically we would use a matrix of flows to calibrate a global spatial interaction model. And by that I mean we would calibrate a model with which would have one set of parameters, and we would get an estimate of each one of those parameters in the model from a matrix of flows. So this is a very small matrix of spatial interactions. It's journey to work flows in the metropolitan area of Lausanne. It's 70 by 70 matrix. So it's only got 4,900 flows in it, not very many. But what we typically would do is take all of those flows, calibrate some sort of a spatial interaction model. Here, for example, a very simple Poisson model, where we have three variables, just as an example. We've got an origin repulsiveness variable, in this case it's economically active population. We've got a destination attractiveness variable, it's the destination number of employment opportunities in each destination zone, and there are 70 of these zones. And then we've got the road distance between them, and we've got a parameter for each of these three variables, which is estimated from this data set on 4,900 flows minus the 70 interzonal flows. And that's typically what we do. Obviously we might have more of these things in here, but that's a reasonable description of the kind of classic type of calibration of a gravity model. It's okay. It gives us some information on people's deterrence of distance. It gives us some information on the attractiveness of employment opportunities. It gives us some information on the degree to which people move out of certain zones in the morning, certain residential zones. But that's it. And it gives us a very broad brush approach to information on the processes operating in the Lausanne metropolitan area. There might be, for example, differences in these processes from east to west or north to south, or along certain communication lines, etc. We don't know that, because all we're getting are these kind of average parameters. So, two questions. Are we able in some way to disaggregate this system so that we can estimate more parameters, get more information on the processes generating the data? And ultimately, is it possible to calibrate a spatial interaction model for a single flow? Instead of using 4,900 flows to estimate three parameters, can we calibrate that model, the same model, for a single flow? Now you're all thinking, that's just ridiculous, you can't do that, that's impossible. Okay. But let's just see how things go. Okay. Right, okay, so comments on spatial interaction models. Spatial interaction is the movement or transmission over space resulting from a decision-making process. The movement involves physical transfer, the transmission involves non-physical transfer. So, and it's very applied, so that again, this is a useful conference to come and talk about spatial interaction, because spatial interaction models have seen a great number of applications. Possibly, you could argue, they've been one of our geography's most successful applications outside academia. There is physical movement resulting from a decision-making process. Examples of that are things like retailing, migration patterns, commuting. There are non-physical movements resulting from a decision-making process. Examples include communication, information transfer, knowledge transfer, etc. Those are examples of spatial interaction, according to my definition. There are other types of movement, physical movement, for example, which does not result from a decision-making process. Things like storm tracks, movement in storm systems, forest fire, disease, contagion, pollution, diffusion, etc. Those are typically not counted as spatial interaction model. We normally look at those through various types of trajectory analysis, etc. But these are, and there are lots of things which fall within these two definitions. Spatial interaction models have a very simple framework. They tend to look at the flow between an origin and a destination as a function of a set of origin attributes, a set of destination attributes, and some measure of spatial separation. And the idea is we construct a model of this general form and obtain accurate estimates of the parameters of this model for each relationship that we specify, in order to inform us about the processes affecting the flows, generating the flows that we observe in the real world. And by doing that, we then can have a better understanding about what causes different volumes of interaction between different origins and destinations. And then we can try and influence those flows in some way. We do in retailing, for example, we try to attract more people to our shops than to our competitors' shops, etc. Or we could look at trying to influence the migration flows through various government policies, etc. So I'm going to take a very, very simple example of a spatial interaction model which follows that general format I've just shown you. We don't need a complex model because it's going to get complex enough anyway. So we're going to take a very simple model where I've just got one origin attribute, one destination attribute, and one measure of spatial separation. And we've got the flow between I and j. We've got vi raised to the power alpha as our origin attribute, wj raised to the power theta of our destination attribute, and dij to the power beta as our measure of spatial separation. And we're interested in obtaining estimates of the parameters alpha, theta, and beta, and obviously k as well in here, to give us some information on the processes generating the flows that we observe. And a typical spatial interaction model matrix is comprised of the following elements. We've got cell counts of the flows, we've got a set of origins, a set of destinations, we've got therefore total inflows into each destination, we've got total outflows from each origin, and we've got an overall total amount of movement in the system. And what we want to know affects in some way, or determines in some way, the kind of model that we might want to use. So for example, and there's a well-known family of spatial interaction models, which Alan Wilson was one of the proponents of. For example, if we have an unconstrained model, then we can use that to tell us something about the future flow matrix, about total inflows, about total outflows, what makes a destination attractive, and what makes origins repulsive. If we take a production constrained model, it'll tell us something about the future flow matrix, total inflows, and what makes destinations attractive. It won't tell us anything about what makes origins repulsive. It's production constrained. An attraction constrained model is a mirror image of that. It would tell us something about the future flow matrix, it would tell us something about total outflows, and it would tell us what makes origins repulsive. It wouldn't tell us anything about what makes destinations attractive. And finally, a doubly constrained model would tell us something about the future flow matrix, and also the role of distance or spatial separation in determining flows. So you can look at that and say, well, okay, well, obviously, why don't we all use unconstrained models, which we don't normally. And the reason for that is, if we look at the accuracy of these models, the accuracy of this kind of model is very low. Typically, the accuracy of this model is very high, but it doesn't give us very much information. So we typically use one of these two things in the middle, which is a nice mixture between giving us reasonably accurate information on a reasonable amount of attributes of the spatial interaction modeling system. In fact, those four models, which we all talk about being as part of the members of this family, are actually just four out of an infinite number of models. They're the corner points of this diagram here, which is the Alonso framework, and simply putting in different values of alpha and gamma in the Alonso framework, setting them at 0 and 1, gives you the four corner points, gives you these four members of the traditional family of spatial interaction models. But indeed, you can have an infinite number of spatial interaction models by putting in values of alpha and lambda, between 0 and 1. These are quasi-constrained models. There's an infinite number of them. So there's lots of spatial interaction models we can have. However, all of these, and there's an infinite number of them, all of these models that we're talking about are global, in the sense that we are using all of the spatial data available to us to estimate one parameter for each relationship. So we've got a set of origins and destinations, origins being round dots here and the destinations being square dots. And we take flows between all the origins and all the destinations, use them all, put them all into a routine, bit of software, and we estimate the parameters of our model. But what if the processes, the determinants of interaction, vary over space? We have no idea of that. We're just getting one set of parameter estimates. So there are quite simple ways to get around that problem, and they've been around for decades now, by just making disaggregation, spatial disaggregation discrete. We can have, this is the second section here, we can have spatial disaggregation by origin or by destination. So each spatial interaction model can be calibrated separately for each origin, each row of the matrix, or for each destination, each column of the matrix. So there's an origin-specific model, where we've now got flows out of origin I are a function of the attractiveness of J and the spatial separation between I and J. And we estimate two parameters here. We estimate theta I and beta I. Those parameters are specific to origin I. Obviously, we don't have any destination characteristics in this model because it's an origin, sorry, we don't have any origin characteristics in this model because it's an origin-specific model. It flows out of one origin. There's no variation in the origin attributes. We've only got one origin. So we lose something, but we gain parameters which are specific to each location, each origin. the destination-specific equivalent, which is the mirror image, where the flows into destination J are a function of origin I attribute and a spatial separation attribute. And we get parameters, alpha and beta in this case, which are specific to destination J. And clearly, in this kind of model, we don't have any information on the destination attributes. This is only one destination. But we do get destination-specific parameter estimates. So it's a bit of a trade-off. But this gives us more information. So we've now disaggregated the parameters. So we've now got, in the Lausanne case, we'd have 70 sets of parameters here for the origins and 70 down here for the destination. And that would generate some interesting information. Now, can we go further? And this is where, depending on your point of view right now, it either gets interesting or it just gets hopelessly confused and rather boring. So let's see how this goes. Right, fuzzy location. This is the sort of slightly newer bit now. How can we approach this a bit differently? Well, first of all, we can have what are called fuzzy origin models, where there's our interaction system. We've got a set of origins and a set of destinations, flows between them, etc. And the question we pose is, there's a location, an arbitrary location in space. It's neither an origin nor a destination. Doesn't matter. Doesn't matter if it is, doesn't matter if it isn't. But there's a location in space, just call it X. The question is, what's happening around that location, around that place X? In terms of spatial interaction processes, can we get any information about that? Well, yes, we can, because we can weight the flows. In this case, it's a fuzzy origin model. We can weight the flows according to the distance of each origin from X. Just as we do in a geographically weighted regression, we have exactly the same principles, the same kind of kernel routines, optimization procedure for the bandwidth, etc. The same thing applies exactly, where all we're doing is weighting all the flows out of each origin by the distance from each origin to location X. And we're using those flows, those weighted flows, to calibrate our model. And then we can move X around in this space, and every time we move X, we get a new set of local parameter estimates. Because each time we do that, all these distances and the weighting functions will change. So this gives us what I call fuzzy origin models, which look like this. We've now got our parameter set, so alpha, theta, and beta, which are now related to this location I. And this curly bracket here denotes a parameter estimate relating to a region around I. It's telling us what's happening around I, not exactly at I, but it's using data from around I to tell us something about what's happening, likely to be happening at I. So in that case, in that sense, that's my use of this word fuzzy, which can be argued about. Now note, this is different from our origin-specific model because we can include the origin variables in the model. There's no reason we can't. We can just take weight all the origin attributes according to how far away they are from location X, weight the destination attributes, etc., by the origin values and the distances. We weight all of these things by origin distance to X and calibrate the model. So we can do this and we can get a full model out. We don't need to sacrifice the origin variables in this kind of localization. Now, we can go a step further. We can have a destination-specific fuzzy origin model. So we could say, I'm just going to look at one destination. I'm going to look at all the flows into that destination, but I want to know what's happening around this point X. I don't want to know an average of what's happening from all of these origins. I just want to know, for the flows that are coming into my destination, what's happening in this region of space. So again, I can take just these flows, but weight them according to the origin location with respect to X. So those origins which are located closer to X get more weighting. Those origins which are further away from X get less weighting. And I change X. I move X around in this space, and every time I do that, I change all the distances, and therefore I change all the weights, and therefore I change the resulting local parameter. So I can repeat this for each destination as well. So I'm getting lots of parameter estimates. I'm getting a surface of parameter estimates for this specific destination. It could be a store, it could be a city, whatever context we're looking at here. And I can repeat that for each destination. So now I've got a really spatially disaggregated model, because now I've got a model that's going to throw out parameter estimates, in this case alpha and beta, the origin attribute parameters and the spatial separation parameters, which are fuzzified for I. They're a region around I, but are specific to destination J. So I've now got a matrix of parameter estimates instead of a vector. Now I can't include destination variables into this model because it's destination specific. Yeah. But I do have a matrix of parameter estimates. Now the opposite of that is to have a fuzzy destination model. So here we're interested in, we've got a flow system here and we've got a location X, and now we're saying, well, what's happening around X? But we weight the interaction, the flows, by the distance of the destination in each case to location X, not the origin. So we're weighting it by destination, not by origins. But exactly the same principle occurs. We can weight this, and now we get a fuzzy destination model, which looks like this, where the parameters are specific to a region around J. And again, we have a full model here. We can include destination variables within this model, unlike a destination-specific model. And again, we can reverse this and say, well, okay, we can have an origin-specific version of this model. We can have an origin-specific fuzzy destination model. So there's my origin. I've only got one origin here. It's origin-specific. I've got lots of destinations, and I'm asking, well, what's happening in terms of flows from this origin to destinations around location X? So I weight my flows according to how far each destination is away from location X. When I do that, I have this kind of model. So here's the fourth of my fuzzy models, where we have parameters, a matrix of parameters for the destination attractiveness variables, and we have a matrix of parameter estimates for the spatial separation variable. So here they're origin specific, they relate to I, and they relate to a region around J. So we have a matrix of parameters for each relationship in our model instead of just one. Now obviously you can't include, because it's an origin specific model, you can't include origin attributes in this model. And finally, and possibly the ultimate in spatial interaction modeling, can we calibrate a model for a single flow? Well, we can. There's a flow between a specific origin and a destination, ij. I can calibrate the spatial interaction model for that flow by taking the flows around it and weighting those flows according to how far away they are from this flow. Now obviously that's a bit more difficult because now we're talking about 2 dimensions, not just points in 1 dimension. But obviously it's not that difficult. We've got vectors here and we can just do some fairly simple arithmetic to get a weighting of each vector to this one. So if we do that, we get what's called a flow fuzzy model, where we have a full model with the intercept, origin attribute parameters, destination attractiveness parameters, and separation parameters, all of which are in matrix form. Where they're all fuzzified, they're all regions, not specific location. But we've got now a full model where we've got a matrix of parameter estimates for each relationship in our model. Before, when I started off with the global model, we had 3 parameters. Right, we had the alpha, theta, and beta, and I gave you examples of what those were from the Lausanne dataset. Now, when I show you the Lausanne dataset, instead of 1 parameter for each relationship, we've now got 4,900 more information, okay, to deal with. Okay, so now we've got a method to calibrate a spatial interaction model for individual flows. So how do we do that then? We need to weight these things. So there's our, there are various ways of doing it. This is one of the simplest ways. There's our vector in question, there's our origin and destination, and there's another one over here, another flow, there's an origin and destination. Well, we can just put that simply in 4-dimensional arithmetic. We've got coordinates here of our origin of x stroke 1, x stroke 2, and our destination coordinates x stroke 3 and x stroke 4. And there's our coordinates of our other origin and our other destination, and the distance between those two can be given by this. Just an extension of the normal straight line distance. But there are other ways of doing that, but that's an easy way of doing it. So we can compute quite easily a distance and therefore a weighting function for each interaction. And let me give you an example of how this works with data from Lausanne. So in this case, we've got a data set of 70 by 70 of communes within the agglomeration of Lausanne in Switzerland. And we've got journey to work data which look like that. And there's the data in matrix form showing the dominance of Lausanne, which is this place here, and on the top, that's the downtown, the city part, and these are obviously the intra-zonal flows on the vertical axis. So most of this is zeros and ones down here, and you've got some quite large flows up here. So there's our data. Here is the essentially geographically weighted bandwidth optimization. The optimal bandwidth, and this is for an origin fuzzy model, I'll show you, it's about 3 kilometers. So we're taking data from origins about within 3 kilometers of each location X, and we're weighting those according to, between 0 and 1 according to how far away they are from location X. And these are the kind of results we get. So here are, for this Poisson model, an origin fuzzy model where this is the population at the residential zones. The local parameter ranges from about 0.46 up to about 0.92, showing this map across here, the darker reds being the larger values of the local parameters. These are the destination attractiveness parameters, number of jobs in each zone, ranging from, not very much of a range at all, from 0.9 up to 1.02. Here are the distance to k parameters in this region, ranging from a minimum of about minus 1.98 out here. You can see the sort of spatial pattern here. It's very heavy, it's a very strong distance to k in terms of commuting from these eastern fringes into the center. And the maximum value is about minus 1.15 in the center here, near the center. This is the west. Okay. Now we can have a destination-specific version of that model. So, and when we do that, we get a different bandwidth. We have to do the optimization separately for each destination. And that's a map of the bandwidth, the optimal bandwidth for each of the 70 zones in the system, ranging from about 1.7 kilometers up to about 35 kilometers. And when we do that, that's the kind of result we get. We get a matrix of parameter estimates for each variable, each relationship in our model. This is a matrix of parameters 70 by 70 for the origin population, the residential population. And the darker values range up to about 1.1, well, I don't know what it is, it goes up to about 1.3, 1.4, I think, the darker reds. The lighter ones go down to about 0.5, 0.6. So you can see the variation across there. It's clearly linear in the pattern because it's destination specific. These are origins and these are destinations in this case. It's a destination specific model. So you can see that's why you've got stripes across here and not much variation the other way, because the origins are the fuzzy bits, the regions around origins, and it's destination specific. You do see some variation. That's the distance to k parameter for this model. Again, we don't have one, we have 4,900. And again, you can see the pattern in there of distance to k being much stronger, being much more negative for these places down here, and much lighter for these places up here, much less negative. Now, I can show you the similar results for a flow fuzzy model, possibly for the first time ever. Here are now a matrix of parameter estimates from our flow fuzzy model. This is the origin population variable. You see it's much more checkered because it's not specific to destinations in this case. We've got, again, Lausanne is the first one on this top row. So we've got origin, residential population, the influence of residential population on outflows from our spatial interaction modeling. And again, the darker version, darker colors are the higher values. It's up around 1.1 for the strongest values, down to about 0.6, I think, are the lowest value. So you can see regions of the country